Uh, Welcome back. So I pulled up one example of a manual flight just to illustrate again why you still need manual flights here. So this is the underside of that truss bridge, and you can see there are parts underneath that even if you're doing a flat parallel scan, you're not going to be able to capture, like these inside parts, right? Because there's this cross beam that is going to obfuscate that view. And so we're going to have to fly inside like so that we can get above it and then look at that defect. And we looked at the past inspection report for this bridge, and some of the main defects were actually in those regions, right? So you can do all of this photogrammetry and you're left with no useful information still as far as doing these inspections. So that's why it's important to plan out what parts of the bridge are most important as well and incorporate that. And if there's no way to do it, then you need to do it manually. So here you can see on the left, this was taken in 2023. And last year we did this inspection with the Skydio, and you can see the same region here. This is a little blur, but the actual image is not this blur. And then here as well, you have another similar kind of region, and we can get that as well from the drone. So that's something that also needs to be accounted depending on what your objective is with your data collection. So I showed you the slide on image overlap. Typically, those of you in remote sensing, you guys know this already. You want to have a high enough overlap so that you have enough features between your images that can be matched, so you can obtain the camera points and the 3D points, and that number is usually between 75 and 85%. So that means 75% of the image 1 and image 2 are looking at the same part of the scene. It's also, like I said, important to build transitions, right? If you have parts of your scene that are changing rapidly as you move, then you want to be sampling much more in those parts. So if you're trying to turn the corner, then the views change drastically. So you have to have more views there to make sure that you're not missing out and you can transition properly. There are actually these days guidelines that that people put out for different kinds of applications. For example, this is from Skydio. They say, for example, if you're doing construction in the construction industry, if you are trying to measure asset damage and so on and so forth, a GST might be 2 millimeters, and then your overlap side lap 80-70. These are useful, but again, they're not taking into account the specific details of the crack size that you need to be measuring. So you need to be able to make those computations yourself based on what outcome you're looking for. To summarize some points to consider, the factor of safety. If you're relying on GPS, you want to test how accurate that GPS in some open areas, and then slowly get it to congested areas, and then account for that appropriately. Distance to surface, presence of obstacles, image overlap, number of loops, and speed. Speed is also another factor that you need to decide when you're flying. When you're doing flights manually, also you can have the option to set the speed, set the max speed. So even if you throttle the drone to one side, it's only going to stop at the max speed. Now this can be problematic because if you need to get out of an area quickly because of an obstacle that suddenly emerges, say there's a bird or something, then that's a problem. So you have to be able to quickly change that. But if you're flying very fast manually, then that can create the blurs. So you need to stop and take photos, or you fly slowly, but that takes longer. So these are all decisions you need to think about in advance and see what's right for your application. Now, without any GPS or without ground control points, you don't get any real world units because there's no scaling factors. If you can get some information from the camera parameters, but typically you need some real world reference to get accurate point clouds in terms of metric units. And there are two ways to do this. One is you can know in advance your camera locations, which is your extrinsics, or you can know in advance your object locations. If you are doing the latter, then you will set what is known as a ground control point in your scene, which is a point of known features and known location. That means you need to accurately measure the location of that ground control point. If you are referencing your reconstruction to a particular asset that you already have measured, then you can use features from that known asset as your ground control points. Otherwise, you can lay down like known targets and measure those locations using some traditional surveying method and use that as your reference. Now, most commercially available drones, they come with GPS, but this GPS is not reliable. The type of GPS that these drones have is similar to the type of GPS in your phones. So here is a simple illustration. I set this point on the map, and then with my phone I walked to that point and saw where it said that point is, and you can see that there's a distance between those 2 points, and the error is on average 2 meters. Average of 12 pixels is about 2.15 meters, right? So it's similar with the UAV GPS, the regular GPS that you would get, and depending on how accurate you want your scale, that may be sufficient or it may be insufficient. If you're trying to do sort of terrain mapping, or you're trying to do a large area, 2 meters is probably fine. But if you're trying to do small cracks, you want the crack width accurately, then that 2 meters may be a problem because your crack width may be off a little bit. Now, this can also be useful to know and to take into account when you are doing your reconstruction, because most softwares, they use the GPS metadata in the images to do an initial the initial estimation of the camera posing. If you have an accurate GPS measurement, then you can further constrain how far the cameras can move from the positions that were captured. But if you do that and your GPS is not accurate, then your reconstruction will be compromised. So here is an example of a scan that we did, and there's this factor called the dilution of precision, where you can set a value in meters to decide how much the precision can be diluted. And you can see somewhat that if you set a higher value of dilution of precision, the overall reconstruction is much better compared to setting a lower value. In lower value, the cameras are restricted, and so it does not allow for the photogrammetry process to discover more accurate camera position. On the other hand, if you set it to be more accurate and you have accurate GPS coordinate, then you can do this faster, and it gives you a better match. So if you have RTK GPS, it makes a big difference. So what is RTK GPS? It's real-time kinematic GPS, and you essentially have a base station, which could, it can be something that you yourself have, or it can be something that's coming from a cell tower or something like that. And that acquires a high accuracy GPS location, and then that is used as the basis for improving the GPS measurements from your drone. So these systems tend to be more expensive. Traditionally, these days you also have more cost-effective versions, but again, you get what you pay for. But if you do have it, then it can be very useful with the photogrammetry process. Like I said, the other option is to use something called a ground control point, and so this is basically an identifiable feature that you affix to certain points that you know the location of, or that you want as your reference. So if you set these locations, then you can take pictures. Make sure you take pictures of those points in your scan, and you want to take, again, multiple pictures of that point in your scan. And the more you have, the more you can mitigate the overall error, but that's only up to a certain point, after which they're not that useful. Because again, they're not affecting your overall reconstruction, they're just affecting how you scale it and how you reference it. So once you've done all of that, then you can execute what you've planned, right? It takes all of that, you need to plan all of that, and then you can execute, and then you can produce your reality model. There are things that you can do to further help pre-processing steps, such as normalizing the lighting. If you have very high dynamic range in your images, that can be a problem for some feature matching algorithms. Of course, these days they're better at that, but still, if you have too much of a difference, then it's going to be a problem. You do want to go in and remove images that are not good. So if you have blurry images, you have very dark images or very bright images, you want to fix them or remove them. And then you can process the data using many of the tools that we'll look at. And then you can also, on the images, you can run deep learning models. We'll look more at that tomorrow. For example, Bentley iTwin, it has a crack detector model inbuilt, so you can use that, or you can use your own models, and you can highlight the locations of these defects. I think we covered that already. Yesterday there was a question, so I sort of answered. I already went over these topics, but just to recap, lighting, it's better to collect data on cloudy days if you can. But otherwise, mornings are typically the best time because you have more diffuse lighting in the morning. And again, with the lens, you want to keep the focal length constant. That's very important. Fixed lens options are very good for that. Finally, you also want to make sure that what you're doing is correct. And so it's always a good idea to try to validate. Here, we put some cracks of known dimensions, just stuck them on the bridge, just so that we can verify the size of those cracks after we do the scan. So we know that if this crack measurement from our scan is good, then probably all the other cracks, or at least some of the other cracks, are going to be good as well. So you can see here that we printed it, it's 5.27 millimeters, or actually when you measure it, you can see it's between 5 and 5.5, and you measure it from the model, it's 5.27, and even for this tiny crack, the model is able to do a good job. So if you follow all of what we discussed, then you can make sure that the data you collect has the properties that you want it to have. Okay, there are some common modes of failure also that is useful to know so that you can avoid trying to experience that. With civil infrastructure, this is a big one because buildings tend to be regular. Bridges, trusses can have very similar components. So sometimes the feature matching algorithms have incorrect matches because of these repetitive patterns, or you have very symmetric structures. You can also have open loop error accumulation. So if you don't close the loop when you're doing photogrammetric scan, then it's difficult to ensure that the bundled adjustment that you do, where you optimize for the camera and the poses, camera and the points, results in accurate geometry, because part of the optimization process, well, the optimization process can lead to drifting, and the way to correct for that drifting is to have a closed loop. So that's why it's important. If you have varying distance to surface, that can also result in errors accumulating. Moving objects also will result in different views or different representations of the same part of the scene in different pictures, because there's this thing that's moving, and shiny transparent surfaces result in optical effects that also confuse the feature matching and make it harder to reconstruct. And of course, if you have textureless surfaces, that can also cause failures. Here's some examples. This is a reconstruction of the Big Ben monument in London, and you can see that the orientation of some of the buildings around it, around Big Ben, is different in these reconstructions, and that's because the different faces of Big Ben, they were designed to be extremely symmetric and very similar from all sides. And so if the feature matching is using just the clock, then it can get confused to which side that image is coming from. Here is another example, because of repetitive patterns that you can see on this surface. Even though the camera is looking at a different side of the circular structure, it's the same pattern, so it's getting confused as to where the matches are. And so you can see that instead of closing it, the cameras are estimated as being outside. And if you have similar patterns, then you can have incorrect matches as well. So these are both corridors, and there are some corners of the ceiling tiles that are matched, but they're different corridors, and so that results in problem with the reconstruction. And like I said, if you have if you're able to close the loop with your reconstruction, then that can again allow you to improve your overall reconstruction. Another point is that when you're using these photogrammetric packages, if there's misalignment between two, or if there's one chunk that's misaligned, then you can also use something called a tie point, where you manually go in and you say, okay, this image feature in this image corresponds to this feature in this image, and you say this is the same point, and you give a few of those constraints, and then it can close, and you can create your model. So this is one example. We had to do this for the Main Street Viaduct Bridge. You can see here that it was creating two versions of the arch here, and by adding a few manual points, we were able to fix that easily. So I think this slide was supposed to come before the last one, but here you can see examples of how they were able to, in this paper, they used extended features to reduce drift in closed loop surveys. You can see examples of different features. So CoalMap is an open source photogrammetry or structure from motion package, which is very commonly used in computer vision. And you can see that it's not able to close the loop, CoalMap, but using different features, they're able to, or they've proposed a new feature that allows them to address that case. Okay. some other points to remember: you want to have at least 3 photos or for each point, and then 60% would be the absolute minimum overlap, and then 15 degrees if you're making rotations, and then you want to make sure to take the transition photos. Use manual type points, keep a constant focal length, adjust lighting, and reduce error accumulation. So these are some software packages that are available that allow you to do this. It's not an exhaustive list, but these are all available. Not all of them are free. The ones on the left, actually, they're all free. The ones on the right, the first one is not free. The second one used to not be free, but now is free. So we can use it. And that's it. Any questions about this before I show you a demo of the reconstruction? Yeah, so it's a good question. Why do you need many ground control points? So the goal of the ground control points is just to do the referencing, and if you have more, then the chances of you you're able to average out any errors in the ground control points themselves. And there can be errors in your photogrammetry reconstruction, and so even if you know the exact location of the ground control point, its reconstruction with respect to the rest of the scene may be compromised. So if you have many ground control points, then you are mitigating that error. But again, like I said, there's a limit to how useful it can be. So people typically have, between 4 to 12 ground control points, not more than that. Say that again. Some drones come with RTK GPS, like the new, some of the new DJIs and the new Skydios, and even other manufacturers, they come with RTK GPS. So GNSS is that the it's a good question. Does anybody know you know the answer to that? Yeah, you want to answer. So just in case those online didn't hear, GNSS is a general terminology of the kinds of systems that GPS is a type of. All right. If there are no other questions, so how many of you were able to download reality capture? Okay, that's a decent number. Let me share with you a link to a data set. If I put it on the WhatsApp group, you guys can access it. So that's the Epic Games launcher, and there's reality capture. So do you guys have it? Are you guys able to download the data set? It's taking some time. Yeah, that was the smallest one. Everything else is bigger. The data sets that they have are like several gigabytes. So that was the smallest one. That is sort of related. There are some smaller ones of just how many minutes for the rest of you? If you have any problems, you can say it. I just want to know what the status is of the table. All right. For those of you that don't yet have it downloaded, you can, I suppose, watch what I'm going to do. So I already have it downloaded. And to start, actually, I'm going to go to the settings. So if you go to workflow, you can go to settings here. And then you can choose your coordinate system. So choose the EPSG 4528, which is commonly used. And let's see. I think for now that should be fine. What? The project coordinate system, you can choose EPSG 4528. If you just type in 4528, it should show up. It's already selected in mine because I already chose it this morning. Okay. How many of you have the data set? Oh, all right. So you can go to add folder and you can just import your images. So here I'm going to go to images and then say select folder. And then there are 482 images. You can look at them. So I can change the view here. So I can change this from 3D to 2DS. So 2DS allows me to create a grid of all the images, and you can see what this looks like. It's basically a construction site. I can also have this split view where I can view individual images. And you can see that these are all taken from above, right? So they're all nadir views. I'm going to go back to this view. Thank you. Okay. So you can see the focal length of all of the images. How many of you are at this screen now? All of you have the images loaded. Then all you need to do is click on align images. And this part shouldn't take too long. So this is where the initial camera calibration and the point cloud reconstruction takes place. This is called a sparse point cloud because it's not trying to get all the points, it's just trying to get whatever points it needs to also get the camera localization. So it does the alignment and then it does the feature matching and then it computes the camera poses and the points. And in a few minutes, it should have, like in 2 or 3 minutes, it should be done. Yes. Yeah. Just this. Yeah. So you can also import GCP files subsequently. Are we using the Teams? Yeah, but are we recording? It's not recording. Oh, in the software it's, oh, I see. The internet connection on my laptop is not stable. Sorry, guys. Share window. So we can wait for that to happen. Now there are some ground control points here, but this morning when I tried it, I had some issues with the ground control points that they've provided that I was not able to resolve. So I'm going to skip that part. Okay, but if you were to do it, I'll show you what you would do. So before we get there, you can see now that I have this reconstruction. I can pan and view things, and you can see that there are a lot of points. There's some parts where there are not as many points. In this region, not as many points. Why do you think that might be? Let's look at some of these pictures. So why do you think there are not as many points in this area? Seems like this is the area where all the vegetation is. This is the house here. See the roof. But the area where there's no reconstruction, that's the vegetation. So of course this area is, the elevation is not visible because the trees are blocking that. So there are limits to what you can see from these sorts of views. But if you want to get some measurements, then this might be okay. Okay, did anybody get to this stage? Yeah. Do you guys have GPUs on your computer? Yeah, you do. Does anybody who doesn't have a GPU, did they get to this stage? I'm just curious. You don't have a GPU and you didn't get to this thing? Oh, okay. So if you're happy with this, then the next step is to just densify. But if you want to make some changes at this stage, say there are some parts that you're not interested in, you can change the scan volume, right? The volume can be changed. You can also make some edits after you do the reconstruction. So to do the dense reconstruction, you would just choose one of these. So I'm going to choose normal detail, but I'm not going to choose it. Instead, I'm going to cheat and open what I did in the morning, which is just open this dense reconstruction. Let me save this just in case we want it again. So I'll call it in class. And now I have this dense reconstruction. And you can see that it has reconstructed these trees. It's missed some points here, right? Maybe those features were not, because of the trees, the features were difficult to associate. But the roofs, it gets pretty well. And also the roads are good. Now that we have the mesh model, what we can also do is modify it if we want to. So say we want to clean it up. Say there are parts of this mesh that I don't want. I can get rid of those parts, right? So I do that, and then I need to filter it. Should be a section for filtering. Let's see here. Region and sparse function. Filter selection. So if I click on that, then it's going to create another component, and now you see that that section is gone, but it's still here, right? So if I want to show the previous one, I can, or I can use the new one, right? So you can simplify your model as much as you want. Say I'm only interested in for now, say I'm only interested in this building and the region around that. Let me make a selection there. So if I go back to tools, I go to lasso, then I can make a selection just around this, and let me add a little bit. I think there's a way to add to your selection as well. If you hold control, then you can add to your selection. And then I'm going to invert it, and then I can filter just that part. Okay. So now I can zoom in just to the part that I want, and I'll switch off the lasso tool. Any questions so far? How did I cancel? Densify. Oh, yeah, I use this normal detail. You can use different levels. There's high detail preview, and you can go to settings and change the mesh calculation details. But that takes about half an hour. So I just did it in the morning, and I'm showing you what I did in the morning. Is it saying that? Are you asking me, or are you telling me? That's what I do. I'm not sure, because I have a GPU, and on their website it says you need a GPU. That's what. Is it saying that? Yeah. So that's what I figured. So if you really want to do it, you can download Alice Vision. It'll be much slower, but with the GPU, it only took half an hour to do this whole scene. So it's pretty fast. No, it's the same process as the structure from motion, but now you have the camera, and there are you can obtain more points in between your sparse points by looking at more features, because now you already have the alignment, so it's easy to get more features. And if you get more features, then you can match more features, and then you have the camera poses already, so you can solve for those locations. So yeah. Yes. virtual reality. I think that's just advertising on there. It's actually doing something. No, I didn't click the start button actually. What I did is click the align button. Yeah. If you just next to the start button, you see align images. That's. I don't know what happens if you click start. Maybe it tries to do everything. But that may take some time. But you can experiment with it. It's for if your company's revenue is below $1 million, then it's free. Otherwise, you need to pay for it. That's the, something like that. You need to read their terms. It's free, I think. So then we can do the texturing. So this will, do this process. Right? You have the mesh. It creates a UV map. It has the correspondences, finds the overlapping patches, puts it onto the atlas. Should be possible to, let me see if I can find those files. They're all in DAT files. Yeah, they're all in DAT files, so you can't really access that. But we will, saying it's going to take a few more minutes. Let me pause it and I am going to open what I did in the morning. You have to do it after densification because you need the mesh. If without the mesh, you cannot get the mapping and you cannot get where to project it because you can project colors onto the point cloud, but you can't get a texture map unless you have a mesh. So a mesh is a prerequisite that you need. So, align, densify. Well, align, and then ideally you want to do the GCPs after that. So how do you do the GCPs? Let me show you that as well. So there's some unassigned control points, but if I were to add ground control points, I would choose these points. So let's look at that to understand what it looks like. It's not going to work now, but the process is still the same. There's something wrong with the ground control points, I think. So here you can see the number of the ground control point. You can see coordinates. So this is north and east latitude and longitude. And then you have the altitude. I downloaded this from the site, but I don't know. I'm assuming this is in meters, right? Altitude probably meters. It doesn't say. So that is, those are the ground control points. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points here. These, so what is this? Altitude. So it's a physical point on the earth, right? And these are different numbers of names for the points, 101 to 203. Now that has to be associated with your scan somehow, right? We have this other file here, this CP measurements XY, that does the association. So here, what do we have? We have image name. We have which ground control point is visible in that image. And then we have X and Y. So what are these units for these pixels? Right? You have pixels X, pixels Y. And then you have the image, and you have the ground control point name. Yeah, on DJI_0533.jpg at pixel 1803.8, 370.45, you have ground control point name 102. What is ground control point name 102? That is, let me find the right. So actually, it's not an Excel file, it's a notepad. You have 103 is that 49.02, whatever. Okay. So if it's working, then you should be able to import this, right? And when you import it, it's going to ask you the format. So what's the format of our thing? It's north, east, and altitude, and then it has spaces. It's EPHG 4528. I don't know, but that's what I'm guessing from looking at that, and maybe that's why it's not working. But that's my best guess. So now you see these ground control points here. Now I just have the locations imported, but I need to also assign the ground control. So for that, actually, I need to do the control points. And for that, I will take this file. And then here I have images point XY spaced by comma, which is correct. And I can choose my measurement accuracy. I don't know what it is for this survey, but I'm just going to leave it as 4. Now you can see the errors are very high. So there's something wrong with this. And you can update the alignment, right? I go to alignment, I can update it, but it doesn't seem to change the errors, which is what it should be doing ideally. So you can see the ground control point 101, right? We can look at that in this image. You can see 101 there. So we can zoom in to see what that looks like. You can see there's this marker. And it's the same for all the other points that they have. Now, ideally, this error should be in centimeters, not in that. So there's something off here. I think maybe some of the settings, or I don't know, because I followed their instructions very carefully, but this is what I got. So maybe something wrong with. So there's this. Something is off, right? And I wasn't able to debug that, but anyways, not to worry. It still doesn't hamper the objectives of the course. Now, even without the accurate ground control points, because there is GPS data from the drone, we can still make measurements with this model, right? How do we do that? Say I want to measure the width of this road. I will go to tools and say define distance. And I just need to select points, one here, one there, and that's 10.45 meters. Seems about right. I need a mouse here. Sorry about that. Now let me unselect this define distance, and then I can move. I've lost. I need to reset the view somehow. scene alignment. Scene 3D view, and then there we go. Okay, so I don't know, I think the distance that I measured is here, right? 10.45 meters. Now we know the location of this thing, so I can pull it up on Google Maps, right? 4918, the same site. And I think this is the road, and we can measure this on Google Maps. Yeah, so it's about 10 meters here, right? I don't know if I got the points exactly the same, but in our model it was 10.45, similar, right? So this is just with the drone, because of course with my ground control points there's something off about it. But you can see even without that you can still get some reasonable measurement. Questions? Yes. No. So the GCPs are already referenced, right? If you open this file, that's what I said. You have accurate locations already of all the GCPs. And you have the associations of the control points in this file, in pixel units. So if anybody knows why it's not working, let me know. But even without that, I think the point is made. And of course, you can also measure heights of the building. That you can't do with Google Maps. But even though this is just a nadir scan, you can also measure the height. I'm a little slow without a mouse, but if I get there, then you can see wait, I need to go to mesh, tools, define this. There we go. So the height here seems like it's 9 meters. Maybe it's easier to measure in the corner. It's 7.47 meters. That also makes sense. But that's what you can do. Now, if I zoom in, you'll notice that there are some distortions here, right? It probably doesn't look like that. And these parts, right, below the extended out roof, those are barely visible in any of the pictures, so you shouldn't be relying on those parts. But these haystacks, they look pretty good because there's no occlusions. This one is it's a little muddled. But that's the idea. Any questions about that? If not, I don't think I have too much else on this topic. No, I knew the GPS coordinate of the ground control points. Maybe there's a way to get the GPS coordinate here, but actually it's not associated with the GCPs correctly, so I would not trust that. But what I did was I just went to this point and I just put in Google, and then it found that for me. Okay. So maybe we can take an early lunch, and then we can go to the drone flight in the after lunch. And tomorrow I'll get started with deep learning. The idea is that you have all these images, right? And you can put them into context using photogrammetry. You can make measurements. But here, even in this scene, the textures are not that reliable. So you still want to work with the images, but if you're searching through a lot of images, then that's difficult to do manually. If you can have automated detection that can also allow you to do automated measurement, automated documentation, and that is a much more convenient record of the asset if you want to refer back to it at a later point in time, or you want to see how things are changing. And so that's what you can do with deep learning. You can automatically identify these defects, but that needs you to build data sets. Maybe we can spend 10 minutes and I can start off with that, and then we can continue tomorrow. Yes. After you do the alignment, that's when I would do the GCP and control points. After that, I do the densification. It's called normal. If you go to mesh, or go to mesh model and normal detail. So that's how much detail you want in your densification. Yeah, so you need a GPU to be able to. But it's yeah. So once you have that, you can export it as an OBJ or something else. You can import it directly into Unreal because they're both by Epic Games. So it's very convenient if you're using Unreal Engine. You can also export it to Unity or whatever other game engine that you want. And those game engines you can also export it to Blender, which is a open source modeling software. And it's useful to have these models in those environments because then you can do more experiments on if you want to refine your data acquisition strategy using a reference, then you can do that in that sort of environment. So last class I showed you this framework for automating inspections, and we looked at this part, and we'll look at it also later, but there's all of these other steps that I spoke about. So the first one is annotations, and this is also very important because if you're trying to train an AI model, the most important thing for that model is, apart from the model itself, is the data that you use to train the model. So you need to give it high quality data that is related to your objective, and that means you need to have annotations. Not necessarily, but if you are having a supervised learning approach, so and we'll go more into detail tomorrow, but in supervised learning you have a specific annotation for every image, and you're basically teaching the algorithm to output that annotation given the image. So for semantic segmentation, you need to annotate every pixel in your image. There are different ways to do this. There's one tool that I had developed many years ago, which allows you to do this with some assistance from some image processing techniques. So say I have this image and I want this to be part of my data set that I'm going to use to train my deep learning model. We'll get more into details about what that model looks like later, but say I want to do that, then I need to, sort of like a coloring book, I need to indicate exactly which pixels correspond to the crack and which pixels correspond to some component, and maybe this is more than a crack. This is a crack, this is some fissure. So maybe I want to give them different labels. If I had to do that manually, then it's very hard to stay in between the lines precisely, and it can be really time consuming. On the other hand, you can use the fact that there's a big gradient change here, and so many image processing filters will allow you to highlight that difference. So here what I've done is I've implemented several different image processing filters, which are very commonly available in a package called OpenCV, plus some additional methods that were developed specifically for detecting cracks. And you can see thumbnails of what those filters look like, and you can choose the one that best meets what you want. Once you choose that, then you have a mask, right? And so this is detecting the crack, but it's also detecting the top of the that parapet, or not the cantilevered portion from that structure. But what I can do then is I can just take the intersection of whatever I'm drawing with this mask, and then I can reduce the time it takes for me to do the annotation. So here you can see that I'm calling this falling, but you can see that the annotation is on the right. Right? Let me play that again. You see, the user is approximately making this annotation, but once they're done, it takes the intersection of the annotation with the mask, and so it simplifies the process of doing that annotation. And similarly for these other parts as well. And then you can go in and you can fine tune it. You can use different filters for different cracks, and you can also change parameters, so that it speeds up the process of making these annotations significant. There are also many other tools. Data annotation is a fundamental aspect of any AI system, so much so that companies have invested billions of dollars into having very good and very accurate annotations with extreme quality control. If you look at the whole self-driving industry, it's all based on human annotations, right? You have Tesla. They have their own whole annotation stack that they've built, which is proprietary, and same for Waymo. And anytime they get new data, it has to be annotated. But of course, you can speed things up, and you can use previously trained models. Also, just like how I used image processing methods, you can have previously trained models. And these days, there are foundation models that do many kinds of segmentations very well. So there's and we'll look at that a little bit next class. There's a model from Meta called the segment anything model, and there are a couple of versions of that, which can also be grounded by text, and so you can get a text guided segmentation of specific things. It doesn't have all the kinds of defects that as a civil engineer we might be interested in, but you can also use that as a starting point to fine tune that model, and then use that fine tune model to help speed up your annotation. So these are some open source tools that are available. We made some data sets using the tools that I described, and you can see here the amount of detail in these annotations is quite high, and we were able to achieve that because of those tools. There are also many open source data sets that you can use to bootstrap models specifically related to damage. So these are some links, and I will share the slides with you. I just didn't have time last night because I have meetings in the night because I'm still on US time also. So even when I go back to my room, I'm still working, so I haven't had time, but I plan on sharing slides with you guys. So but if you need it urgently, then you can, of course, feel free to take pictures. Okay, any questions about that? Again, it's there's no way to understate the importance of data annotation quality if you're trying to build a system that's going to be of use somewhere. Because if you don't have a high quality data annotation and high quality data, then the models that you train are also not going to be good. All right, let's stop there. I don't want to get into deep learning now because that it'll take a lot of time. So I think that's a good place to stop, and can have some fun in the post-lunch session by flying a drone, and can enjoy some lunch now. Okay.